Yeah, so this is my third video, and I'm playing with this thing here, share screen. Mock teaching, mock testing, whatever. But I'm turning things around as usual. This is an environment for tests. Okay, it's used to for exams. Exams are not just tests. Exams do more than testing. And it's called test vision. I never understood the word vision here. But a new vision here is that you can use this environment for teaching. And that's pretty interesting. So I have this problem from the first problem, which was about a 3x3 matrix. In the first problem, the matrix was really chosen randomly and it had an inverse. Here it does not. I counted to 10 and put the numbers in the matrix. And then it doesn't work, the method for the inverse. What is the method for the inverse? Yeah, you put equations, you put general right-hand sides, okay? It's a mathematician's approach to first consider the homogeneous equation. When you put zeros here, but now I put inhomogeneous equations because the basic question is whether or not, if you have three equations for three unknowns, does it follow that you can get the unknowns in terms of these three unknowns? And if that works, it's, yeah, if these are really three equations, then it works for all y, and then different y will give you different x's. So the intuition that you have for this is that the y's should determine the x's, and that a axis y should be equivalent to axis by with b some other coefficient matrix. That's what this should be about from the start. Okay, and then maybe along the way you also want to consider the case that these are zero, and you call it the homogeneous system. Yeah, but yeah. So start with the inhomogeneous system to learn something, and not with the homogeneous system, because then you just lose time. Okay, and then we have a method to find the inverse is row reduction. If it works, it works. If it doesn't work, you find out why it doesn't work, and you learn something. Okay, here we find that it doesn't work, so we will not find this equivalence, but we will find a 2x2b that relates to a 2x2a. How do I know that? Because I did this before, and then I found out. And so you learn from examples. And then I saw in the example that there were two vectors, vectors with two entries, for which this was the case. And this is a structural phenomenon. This always happens. The square matrix that you start with leads to an inverse matrix, which is usually of the same size. And if it doesn't happen, then you have to reduce the problem, and then you still have the same thing going on. You get a smaller square matrix, which does have an inverse. And there's something interesting going on with the variables that you get rid of. Yeah, because this is going to be 2x2. So there's one variable that dropped out for x, and there's one variable that dropped out for y. Okay, so here's the solution method. Row reduce the 3x6 matrix. Here it is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 1, 1. With a forward sweep to this one. And now the editor forces me to put letters here because I cannot put P1, P2, R2, P2, and 3 here because then it messes up here. So I use PQR instead of P1, P2, P3. And what goes wrong here is that the product is equal to 0. And in fact, it's the last one that's equal to 0. Yeah, so important remark, if you did not scale, yeah, so the pivoting consists of row operations where you subtract a multiple of a row from another row. Okay, that's one operation that you can do. You can interchange rows. Okay, that changes the sign of the determinant. And you can scale rows, and that messes everything up if you talk about determinants. So if you don't scale in the forward phase, then the product that you end up with after the forward phase is PQR, and it is the determinant up to the sign, and the sign counts the number of row interchanges. So if you did not scale, then PQR is the determinant up to a for now irrelevant sign, And here the example is that you do not have to interchange equations. So you get PQR plus the determinant. Very important, but because that's very nice to understand this, but not very important here because R is equal to 0. And the sign is your pattern. See how important the sign is. Yeah, not here, it may be for other things. Yeah, and then the end of the forward sweeping phase is that you recognize a matrix, an augmented matrix in which there are zeros here, and the 3 zeros here are important. And then because of the row operations you did and no interchanges, there are ones here, there are zeros here because you only did something below, so the first equation doesn't change, and the second equation changes, but after it changed, it doesn't change anymore, etc. And then the changes, of course, make for additional entries here. It means that if I write the equations again, which is very nice if you put the x's on top of here, then I see P1, yeah, P is P1, Q is P2, those are over here. There's nothing here, so that's 0. And then Y1, Y2, Y3, that's these 3. And then there are entries here, which I call E. E was used for elementary matrices in the part of the book that the program script. Okay, so that's a very interesting part. You learn a lot from it. And in particular, I made a video about what happens if you do have to adjust your method because you run into zeros. And if you do that, then you can either interchange the rows, but it's much more instructive to interchange the columns there. Yeah, because how did you do this? Okay, how did this method work? You looked here, you said, fine, I can use 1 to sweep. I sweep below. And then this 2 has not killed this 5. So there's something else here that you can use to sweep. So it goes wrong in the final step. Okay? If by some fluke this, yeah, after the sweep in this column, this one happened to be 0, yeah, okay, can happen. And then maybe this one is not 0. If it is 0, then you have 3 zeros here. Okay, then you cannot use this one anymore. So you go to the next one. And then you look again at the first one. Okay, if it's 0, yeah, it's 0. And if it's not 0, it's not 0. And then you look at this one too. So it can happen that there are 3 zeros here as well, or just 1 0. But also, if you found that in the after killing the entry, the 4 and the 7 here, the 5 was also killed, then you look at this 6. Yeah, you look at what happened here. If there's a non-zero here, interchange these 2 columns, not the rows, the columns. It's much easier. And that means that there will be interchange between x2 and x3, so that's just relabeling the variable. Okay. Well, if you like, you call x1, x2, x3, maybe some other letter with indices, but then the 2 and the 3 reversed. Or you just interchange them here and remember that you can read off. You put the x2 and the x3 on top to keep track of what you did. I like this. It's nicer. You like to put a space. Let me do some cleaning up here. Now it's nice. We did not interchange rows, so the determinant of A is plus PQR is 0. Yeah, at the moment I'm only interested in this equals 0, and that's because of this one being equal to 0. And then after the scaling, after this, yeah, you have to realize that the row operations do not change the solution set. So now I have a new set of equations which has the same solution set. And the upshot of this is that any pi equal to 0, here it happens to be the last one, leads to a solvability consistency condition on y1, y2, y3. Okay, and non-zero pi are called pivots, and here the pivots are p and q. And now the important thing is that, next thing is that look for nice vectors. Vectors, yeah, so let me, now it's, okay, I'm going to re-edit this. Yeah, there's an important story that comes now, and I will do this with nice typesetting. So I'm going to change these to boldface. And I'm going to have them act on I'm going to introduce another matrix, B, yeah, I'm not going to introduce it. I'm going to recognize it from the calculations that we do. Yeah, so it's hard to miss this B. I'm going to do my best not to ignore this B, like, yeah, it's a choice to ignore it. Yeah? From the calculations, this B will jump into your face. Okay, and then you can let it act on E, F, and G, but for this one I take the unit vector. And then I need indices. So I want to call here E1, E2, E3. And here I want to take a letter, U, V, or W, I don't care, but I'm going to index it with 1, 2, 3. Yeah, and the convention that I take is that my favorite letters for vectors that I chose, yeah, so those are not variable vectors, the vectors that I made. My favorite names are U, V, and W. And my favorite names for vectors which are unknowns, which I think of as variable, are X, Y, and Z. And then you could also think of calling vectors A, B, and C, but maybe that's best to be avoided because we have a matrix which has entries A and another, we have a matrix capital A and a matrix capital B. And if we use names for the entries of the matrix, then it's much wiser to give these entries names that have the same letter. And it's quite common to denote the entries of a matrix capital A by lowercase a with 2 indices. So that's going to be my convention from now on. And that is maybe a reason to always have a matrix either exists of divided by its entries, which have 2 indices, divided by column vectors, which you might then denote by V's, although I don't like that very much, or define it by its row vectors. And that's the way Maple thinks about matrices. Yeah, so if we think about matrices, we can think of them as having entries. We can think of them as having column vectors, which is very useful when you think about A as a map. And we can think about the rows of the matrix, which is very convenient because the row operations are in a one-to-one correspondence with operations with the equations. And after all, this was about solving equations. Yeah, so now I'm going to say stop share. And then I look at the recording. Yeah, I'm going to end this. And then this will be saved to my computer, the hard disk here. And then I put it on YouTube. And this took me, I started this and then I played around a bit. The first movie I will not put on YouTube. The second movie I will, is the longer one, and it ends at 8:16. I'll put it on YouTube, and let's see how long